My name is Iushkevich. I work as a security auditor in digital security, and my role in this research was mobile security guy.
My name is Alexander Bolshev, and I work as a security researcher at digital security. I hold PhD and also lectures at St. Petersburg Electrotechnical University. And my role here was fuzzing and SCADA security consultations. Here is the agenda of our talk. We will give you a very quick and brief introduction to the ICS 101. Then we will review the types of mobile ICS applications, talk about our testing approaches, and finish with example vulnerabilities and attacks that could be conducted with such vulnerabilities. And in the end, there will be a short conclusion. So what is the ICS? In most cases, when you talk about SCADA, you talk about ICS, because SCADA is just a small part inside big industrial control system architecture. Today, you can find ICS infrastructure in every power plant, factory, railroad, airport, building such as business center or a hotel, and even in your house too. In general, ICS collects data from remote stations, also called field devices. Such field devices could be temperature sensors that aggregate some value from the physical world, processes these values, and used automated algorithms, or, if needed, operator-driven supervisory, to create commands to be sent back to the devices that called actuators that do dirty work, interacting with physical world, like switching on/off the pump or closing open gates or so. Here are some ICS samples. I do not know whether you see it or no. On the left, there are several transmitters, the quality of the screen, but you could see the transmitter on the top. And on the right, there is the interface of SCADA system, and in the center, there is a heart of control of every ICS infrastructure, a control room. And here is the typical ICS infrastructure. It divided into 3 layers or levels. On the lowest level, we have PLCs and transmitters that interconnected by industrial buses. On the middle level, you have several servers with SCADA, DCS systems, AMS or OPC software, also human-machine interface devices, and on the upper level, you have manufacturing execution system that interconnect the middle and lower level of infrastructure with the business processes, with ERP system, with corporate networks. Here are some basic ICS terms. We already discussed transmitters. Now it's time to give an introduction to other terms. The PLC, programmable logic controllers, are digital systems used for automation of typically industrial electromechanical process. In fact, PLCs is a special devices with embedded computer inside. They are programming in special languages that are different from C++ or Java or C or assembler. And PLC do all automated things in SCADA and in ICS. So in fact, in real ICS infrastructure, all automated things are done by PLCs. And as for SCADA, supervisory control and data acquisition, they aggregates the whole state of industrial process and show it to the process operator and process engineer, and allows him to do supervisory actions if needed. The SCADA shows full picture of industrial process. Ashima or human-machine interfaces are used to show the picture inside one point of technological process, for example, what is happening on several PLCs, not the whole picture. So I hope now you are a bit familiar with ICS, and let's look at typical mobile apps place in this infrastructure. We divide 3 groups of mobile application. It's mobile HMI panels that resides on a lower and middle layer of the ICS. mobile MES clients that connects to the MES, historian and OPC servers, and remote SCADA clients that connects to SCADA from remote endpoints from the corporate network or through the internet. In the control room application groups, you can see 3 other subgroups. The application that works with PLC and do configuration interaction with them. They are a simple replacement for old-fashioned handheld communicators. In previous years, you need to buy expensive handheld communicator. Now you just install cheap mobile application on your tablet. SCADA clients and mobile Ashima panels. Let's review a bit about every group. So control room application do direct configuring, monitoring, or supervising industrial process or its components. This application resides inside safe or at least firewalled and separate from other segments network in control room. And they have full or partial local control of industrial process. As for MES or historian clients, this application allows engineer and process owner and managers to read and interpret some data from middle or high-level components of ICS. This data is read-only. You don't have direct access to the PLC, Ashima, or SCADA apps in this case, and your only ability is to read some variables or aggregated values. But the most interesting group is SCADA remote control applications. This application allows remote, outside of the safe perimeter or even outside the plant network, monitoring or controlling the industrial process. For all applications in this group, we found pictures, schemes, architecture sketches, documents from vendor where mobile app is shown as remote control unit outside of the plant network. So this is a bit scary, but it is. You can go to some vendor sites and see how they propose application that could be used to do a remote supervising of an industrial process through the internet or through the GSM channel or through other things. And now we will discuss typical attack vectors.
So there are some typical attack vectors. First of all, and I think most obvious, is when someone lost his smartphone or it was even stolen. So it's clear to say that the direct access to the device provides the attacker the direct access to the critical information or even application itself. So he can do all the actions to the ISC server as the operator can do. Another is man-in-the-middle attacks. So someone goes to the bar and connected his device to free Wi-Fi. The attacker can intercept, the attacker can redirect all the traffic through his laptop, so he can intercept all the data between application and server. So, for example, victim decided to change the temperature in his smart house using his mobile application. He sent some data, and the attacker intercepted and changed to another one. In such way, then when the victim returns home, there will be nothing but ashes. Another problem is the unlocked phone on the table. It's clear to say that if someone sees that his phone was stolen or it was lost, he'd do some direct actions. For example, changing his logins, passwords, or if it was installed some SCADA application, he will do it immediately. So let's suppose such a situation when the employer left his phone on the deck unlocked and go to have a dinner or have some rest for a short period of time. The attacker have the phone for direct access for a short period of time. He can try to get some useful information for him. For example, the IP address of the server, credentials, or try to do some malicious actions with the help of the application if it has no password protection. Also, some applications store their data on SD cards. This data can be HMI project files, configuration files, logs, or other sensitive information. So some virus or some another application that have access to the SD card can modify this information. For example, it disable all buttons in the Ashima project file. So when operator try to do some actions using his mobile application, for example, try to switch off some device, he will get no luck. Also, the attacker can try to compromise the remote server with some bugs. It's obvious that server applications can have a wide variety of vulnerabilities, from SQL injections to denial of service and remote code execution and so on. So, what are the main threats for the ISC classification? For control room apps is server-side and client-side DOS. When the server fully trusts the data that comes from operator and the correctness of the entire technological process, fully rely on settings and data that are sent from the mobile application of the operator, the lack of the data validation can result enormous damage. Also, compromise of stored data and that could lead to interface feature modification. It's for HMI apps, for MES, OPC, and historian clients. It's also server-side and client-side DOS attacks. The attacker can sniff credentials or modify data by intercepting or compromise the data protocol between application and server. So it also can badly affect the entire tech process. Cheating operator is also possible. For example, instead of receiving alarm notification, the operator from the server application, the operator receives that's all okay or receive no notification at all. For example, server application sees that sensor shows too much pressure in pipe. And it sends notification to operator that he should lower the pressure, but the attacker can intercept it or do some actions that the operator will receive notification about that he should increase pressure instead of decreasing it, or as I said, he can receive nothing at all. For SCADA remote control apps is also client-side and server-side DOS, process compromise through a protocol, lack of server-side data validation, and a wide variety of bugs in server-side. During our research, we do some steps. There were about 3 of them. And first, we filled up some checklist. The checklist contains some checks and that provide us information about the application itself. For example, how it works, the purpose of it, what it stores, and so on. This information helps us to understand how the application works and what gaps in security can it have. After the entry points were obvious, we begin to file the client side and server side of the application. And in the same time, we do some reverse engineering of it. It helps also us to understand how really the application works and what weak points it has. So let's talk some more about this checklist. During our research of each application, we do some common checks. This helps us to evaluate the application in the security terms. Each checks provide us useful information or actual bugs that becomes the entry points for further analysis. So, for application, it was the purpose of application and what protocols are used. SCADA, HMI, PLC, OPC, etc. Many of them. What permissions are required for application? Using phone services, SMS, writing data on card, and so on. It helps us to understand if the application can be compromised, how it can affect the other applications on the mobile device or mobile device itself. Also, by analyzing its data, we can understand whether the application collects some extra information from the device. Has application any password protection? So if someone lost his phone or it was stolen and attacker found it, can he immediately connect to the server and try to do some actions? Has application any native code? It's obvious that native code application can have much more problems like buffer overflows, user stuff free, and many other dangerous vulnerabilities. Has application any web-based components, so we must do some web checks for it. Protocol. Is there any authentication or the application allows to communicate with server without any passwords or logins and so on? Where with also the authentication on the client or on the server? What protocol is used? What data is sent? Are there any cryptographic primitives are used? And so on. Also, are there any tokens, cookies, or other identifiers sent by application in its request? Does application use SSL? So we should check the settings of it. So, for example, does the application check the correctness of the certificate or has certificate pinning? It allows, this information allows to know whether any SSL-related attacks are able to do. Does application use XML? So, are there any XML parser? What is it? What settings it has? So it also allows to know are there any XML-related bugs can be in the application. And also the server IP. Also it becomes the entry points for fuzzing. And what also for the storage? What data does application store? For example, also HMI files, what connection strings, configuration, logs, and so on. Where it's stored in shared preferences or on SD card. Are this information encrypted? What algorithm used if it encrypted? Just imagine, if the attacker has the direct access to the phone or some configuration files, how fast can he retrieve the critical data from this all? All in all, after all these checks done, we began some more deeply some more layers of the application, and after it, we begin the next step
called fuzzing. Okay, now I will give a quick and brief intro how to do fuzzing of GUI clients, because all applications are GUI. Some applications used vendor-specific protocols for interaction between client and server, for example, some of such protocols shown on the screen. And full reverse engineering of such protocol could take infinite time. To test them easier, we used fuzzing. But fuzzing requires regular communication between mobile application and server. And for mobile application, the problem is that mobile app is a GUI application. In most cases, it won't interact with server without user command, without tapping on some components on the screen. We used a simple solution, Google Android UI Automator, a GUI testing tool to emulate the user taps in the mobile application. However, the next problem arose. Many mobile SCADA applications use native code, C++ or Delphi, compiled for ARM7. And GUI of such application also use native elements, and Google UI Automator standard methods have no support for them. As a solution, we wrote a simple custom extension for UI Automator and used following method. On the first round of fuzzing, we do no mutations, process the fuzzing with correct data. And while doing it, we capture a series of screenshots and put them on cache. We save timings and actions that we are doing and put it all on cache. And on the next round, where we start the fuzzing itself, when we modify the data, when we trying to crash application, we detect the crashes and faults by comparing the current screen with the screen on cache. And we easily could detect the crash. Here is the fuzzing architecture. As a fuzzing proxy, we used Erlang port of Radamsa, Erlamsa fuzzer. And the GUI scenarios also was written in Erlang to do intercommunication with fuzzer more easily. And in this case, we are fuzzing application, and then we are fuzzing server. Of course, it's mutational-based fuzzing, no generational-based. We have no time for generational-based fuzzing, unfortunately. The test scenario example is shown on this slide. The first function creates the tabs on the screen, emulates the user. The second routes the clean chain of user actions and fill the cache with correct actions. And the final function do the fuzzing and check the current state with the clean state to detect the vulnerabilities and crashes and other things. So how it's looked, the quality isn't very good, but here we are fuzzing the mobile PLC handheld communicator to the Siemens Logger programmable logic controller. In final, we tested about 20 applications. Here is the list. The applications are from several types. It's a control room application, mass clients, and remote SCADA clients. And what we saw in the result, it was a bit shock and scary, because control room application, as we've said already, are run in the safe perimeter. So I expected that most of the bugs and weakness will be in control room application. However, most weaknesses and vulnerabilities were found in SCADA remote clients. So the application that connects to the ICS infrastructure from outside of the safe perimeter, that connects through remote endpoints, that could be easily compromised, have the most of vulnerabilities and weakness. And that's strange. I don't understand why it happened, but it is. Here is the test result summary. We have a bunch of authentication problems, have found some crypto problems, SQL injection, denial of services, possible memory corruptions, and SCADA-related bugs. And of course, we can't show you the exact vulnerabilities, because responsible disclosure and responsible disclosure process for ICS application is hard, and fixing the vulnerability could take years. I have a vulnerability in SCADA systems that now fixing for 3 years and still not fixed. So we will not disclose any vulnerability because responsible disclosure, but we will show you the screenshots of these vulnerabilities with cutted vendors' logos and any characteristics that could point you at exact application, but we'll show you something at least.
Okay. About 30% of all researched applications has some authentication problems. Clear text format, some problems with rights, even no authentication itself, many of them. So, in each type of client, there are some authentication problems. So, let's see some of them. First, the plain text authentication. Some applications send passwords, user logins in clear text format. So, if the attacker can intercept this data, he can get credentials very easily and connect to the server and do some actions. So, on the slide you can see the couple of such applications that do so. They even do so over insecure channel. So, if some, as previously mentioned, try to do some actions in bar or free Wi-Fi, The attacker can easily get this information and do some dangerous actions and so on.
Just a question. So before during performing this research, have you been agreed with the SCADA providers, and they provide you with credentials, or you just trying to find apps that belong to some SCADA system in the App Store or in?
We just scanned the App Store because when I first interested, it was in some of our clients. He used mobile phone through the GSM channel, through the private GSM channel that connects to the remote SCADA endpoint. And I was curious by it because GSM channel isn't safe. You can Google and see how GSM could be easily faked and compromised, GSM and GPRS, not LTE, of course. And after it, I go to the Google Play, type SCADA, type ICS, and get a bunch of the application. And it was an idea, what's about security of such application? Is it safe to use them in the real world? And as we said, it's not safe. Let us continue.
So, these credentials was provided by application itself. So, another funny moment. Let's see. While reversing some applications, it helps us to understand how server applications really works and what weak points they had. For example, applications first checks the version of the server. After that, it tries to log in with only username. No passwords, no cookies, nothing. And the server responds with configuration file, and the communication between both of them begins. So with this information, we can understand that if the server is not properly configured, the attacker can get access to it without any passwords, just username and so on. So, if the data is encrypted and all the information that are sent to the server is also encrypted, there are some problems with storing the encryption keys. On this slide, you can see some applications that have some hard-code keys that are used to encrypt data. One of them is Ashima data, other it's configuration. On our side, it's communication data, and so on. So it's clear to say that no matter how the cryptographic algorithm is strong, if there is a slightly possibility for the attacker of obtaining the key, the strength of the cryptographic algorithm in these cases is about 0. It's worth to say that some of these keys are really easy to crack. There are about 6 symbols, but other of them are really pretty hard.
But no matter they store it in the binary, you could reverse and see them in the binary. Or moreover, there are several custom hash implementations. As you can see, this geniusly algorithms. On the first step, you do get the password, get it to the uppercase, and then you iteratively XORing it and do estimation. In fact, the complexity of such key is less than 30 million. So on modern computer, you could crack it in a matter of minutes or seconds or so.
Yeah, really hard cryptography. So, also, there were found some denial service vulnerabilities. On this slide, you can see some Ashima application that helps to monitor the possible big tech process. The attacker can send some packet with some unusual headers and data, so the applications, when it receives, begins to consume all processor
All resources,
Yeah, processor resources.
CPU and memory.
and after some time it begins not to respond. So the attacker, if he knows the IP address of the server, can easily crash the process of the monitoring the tech process.
Cache process.
Yes. But not only server side is vulnerable for the denial of service, the client side is also. Many applications listen to a specific port and send broadcast messages and listen to response. They try to find SCADA server and connect to them in the subnetwork. So the attacker can respond for this request with specific packet that also contains unusual data, so the application will crash. It can use to disable all mobile operators in specific subnet, if you can, in specific subnet. So, also, if you can see this application use the native code, so this vulnerability can cause much more damage, like it can be, for example, double-free vulnerability, and with some research, the attacker can even get remote code execution on the client side. So he can exploit mobile operators in the subnet.
And I want to add something. For example, most of such applications run in background on the phone and receiving some data from the remote system to notify operator if something gone bad. But they listen the UDP port in background, and attacker could silently disable this application just by sending this packet, and application will crash with no notification, and operator could continue to think that application is still running. And at the end of the talk, we want to demonstrate to show you couple attack scenario. The first attack is insufficient validation of input parameters from mobile application, and it happened when server side thinks that all parameters should be checked on the client side. And to craft this attack, attacker either should be connected to the network with target client server in case he should be in control room, or knew the remote control SCADA endpoint and have valid logon credentials. Or if attacker could somehow intercept the connection between client and server endpoint, for example, through Wi-Fi, public Wi-Fi, compromised private Wi-Fi, or through a faked GSM channel, attacker could meet them in the connection with the server, in most simple case, using RPS spoofing, and when a legitimate request goes to the server, it could be modified. I cut the parameter name from this query, so you can Google it, but it could be Googled, in fact. And this query is setting the temperature limit, upper temperature limit. And in this application, we could set the upper temperature limit in home automation room, for example. Of course, this could be set in the factory. This application also runs for power plants. And of course, there will be no catastrophe, of course. The physical controls will be in action and stop the process. However, process alarm or process fault is also dangerous, because if technological process or industrial process faults, restarting the process could cost much money for the business. Sometimes restarting the process after a fault takes days, maybe weeks, or even months. And another interesting attack that is possible is compromising the Ashima software. As we said earlier, several applications store Ashima databases, circuits, interfaces, connection parameters, and project on SD card. If Ashima project data is somehow compromised, for example, by virus, another application vulnerability, for example, if application was compromised through the double free, direct access to the SD card from PC or if the SD card was swapped intentionally, the operator puts the phone on the table and someone quickly swapped the SD card, the attacker can slightly reconfigure or change the Ashima interface. They could replace component events and logic or, for example, sensor data sources. And now the unsuspecting operator is compromised and could make a wrong decision. For example, here is the original Ashima interface of some system. It's a subsystem where liquid goes from one tank to another, and the gauge shows the current level in the second tank. In normal case, the process is fully automated by programmable logic controller, but in case of supervised decision, we have two buttons, stop and start the process. And here is how it's stored. I don't know whether you see it or not. So here is several JPEG images and INI files. And it could be stored in a simple XML-like format. Excuse me. Let you believe that it's XML-like format. Or it could be encrypted but the keys are stored inside the binary, so it could be easily decrypted and forged. And the attacker could reconfigure, and he could connect the gauge to another tank and change the functionality of buttons. Of course, all will be okay. The system will continue to work. But if some event occurs where manual supervision will be needed and engineer will press stop button, but it will start, that could cause some alarm or fault when physical controls will stop the technological process to prevent the explosion, for example, or a huge damage. But also, as I've said earlier, the fault could be dangerous. In fact, it could look like this. Of course, it's a hyperbola, but it could be like this if physical controls are also fail. And here is a conclusion. We reviewed 20 Android applications, and not even one was free of weaknesses and vulnerabilities. The most dangerous consequence of these vulnerabilities is compromising the operator. For example, give him a false understanding of the current industrial process state. SCADA and ICS came to the mobile world recently, but brought old approaches and all weaknesses. And I hope that due to rapidly developing nature of mobile software, all these problems will soon be gone. And we use several tools. For fuzzing, we use Erlamsa and extensions for Google Android UE Automata, for reverse engineer GTGUI and Radar, Wireshark, and several proxies. Here are some links. Up-to-date white paper sources and binaries will be published in the middle of June. And here is the repository of Erlamsa, mutational-based fuzzer proxy. We want to thank Dmitry Yevdokimov, the head of digital research, digital security research group, for some binary magic and great help in reverse engineering of ARM native code, and Marina Krotofil for some bright ideas on ICS threads. And if you have any more questions, we are ready to answer. Thank you.
Thank you.
Thank you.
Let me ask you a question.
Wait a minute.
How many of this application? Could you please get back to the slide with you have a slide with names of applications. It was on the early start of your presentation.
This
okay,
one.
Yeah. How many of these applications were successfully authenticated by you? So you were testing authentication by pass, or just trying to authenticate with default credentials or some brute force with and so on. How many of them were?
Many, I think most of. I couldn't say how.
Okay,
how many.
on next slide
Yes, because of course we could we don't test authentication for control room application because it's a safe environment.
Okay, sure.
It's useless to test the authentication in control room, but for non-control room application, 6 applications failed to authenticate at all. So they use either plain text authentication, either no authentication, or either username only authentication. Their weak SSL and other things isn't on this slide. Other application uses weak SSL, built-in crypto keys, and other terrible things. So most of all has problems with authentication. I assure you.
Okay, I was just curious how many.
Yes. I couldn't tell you what. I think most of them are vulnerable in either one or other way, but I couldn't tell you what exact of this application and what vulnerabilities, because responsible disclosure.
I have a question regarding the vendor response to these. How receptive were they and turnaround for patches?
We've sent several reports already, still have almost no reaction just from Siemens, but Siemens are really good guys and they always do it fast, and even when we publish our brief description to Confidence, they sent me a letter, did you find some vulnerabilities in our software? So they was first and they always do it good. But other still waiting an answer. This could take this could take infinity. As I've said, one SCADA bug that I found 3 years ago still isn't fixed, and I couldn't still disclose it. Okay, thank you again for questions.
Thank you.